Okay, here, so let's find the Maclaurin series for the binomial series 1 plus x to some power p. So again, p is some number. And we're assuming that p is not equal to 0. So, to do this, again, we're trying to rewrite this 1 plus x raised to the power p as a Maclaurin series, meaning the infinite sum, where each coefficient is composed of the nth derivative evaluated at 0 from the Maclaurin series divided by n factorial times an x raised to the power of n. So our function in this case is that 1 plus x raised to the power p. So p is some number we're assuming going into this problem. So p is not a variable here. It is a well-defined number, just for clarification. And we're going to use the same exact table method to figure out, you know what, let's compute the first maybe 3 or 4 terms and see if we can pick up on a pattern for what this series looks like. So let's start with n, say the nth derivative of x. Then the next term would be the nth derivative of x evaluated at 0. And then finally, that nth derivative evaluated at 0 all over n factorial. So let's go ahead and start computing terms. Well, the nth or the 0th derivative of our function is just the function itself, which is 1 plus x raised to the p. Evaluating that is just at x equals 0 is just 1 to the power p, which that coefficient then is just, well, 1 to any power is 1 all over 0 factorial. So that's just equal to a 1. So the first term of our series is 1. Let's go to the next term. When n equals 1, we take the first derivative, and well, here we have a 1 plus x quantity raised to the p, so the p will come down. We have 1 plus x raised to the p minus 1. The derivative of the inside is just 1, so we can just keep that derivative like that. Evaluating at 0, we would just get p times 1 plus 0 raised to the p minus 1. Well, that's still a p times 1 to the p minus 1, or this is still just equal then to p. So the first coefficient is p, whatever that power is, divided by 1 factorial, which is just p. So the second term of our series, or the n equals 1 term, is plus p times x to the first power. Let's figure out what the next term should be. So the n equals 2 term, well, we take the second derivative then, which in this case will just be a p times a p minus 1 from the power rule, all times a 1 plus x raised to the p minus 2 now. And of course, the derivative of the inside, derivative 1 plus x, is just 1. So if we evaluate this derivative at 0, well, that'll just give us p times p minus 1. So that coefficient will just be p times p minus 1 all over 2 factorial. So the next term in our series will be plus p times p minus 1 all over 2 factorial times x squared. All right, let's keep going. What is the next term in the series? Well, when n equals 3, we take the third derivative, which in that case will be a p times p minus 1 times a p minus 2, all times 1 plus x raised to the p minus 3 power. And well, evaluating that derivative at x equals 0, because it's a Maclaurin series, that will just give us a p times p minus 1 times p minus 2. And then that coefficient will just be that, p times p minus 1 times p minus 2, all over 3 factorial. And well, we can start hopefully picking up on a pattern here, where each term we go out, we just get another factor coming from that power rule of p minus some number. And we could keep going like that. So, let's see if we draw on any other observations. Well, like in the next term, if we just predict what it's going to be, well, the next term, we take the derivative, we'll get a factor of p minus 3 times that previous product of p times p minus 1 times p minus 2. See if I can fit it here. And then we'll just take that all over 4 factorial. Okay, well, let's see if we pick up on any patterns. When n is equal to 4, we have a product of p times p minus 1, p minus 2, all the way to p minus 3, as in 1 less than what that value of n looks like. Let's see if that holds in the other cases as well. Well, when n equals 3, we go p times p minus 1 times p minus 2, which is 1 value less of what that n looks like. So let's see if we can write this in another way. So again, the series that we had was 1 plus p times x plus p times p minus 1 over 2 factorial times x squared, plus the next term, which was p minus 1 times p minus 2 all over 3 factorial times x cubed, and so on. And well, we can rewrite this as a much more compactified notation, although it's not going to look as compact as sine, cosine, or the exponential. But we can write this as an infinite series form. Where in this infinite series, we don't have any sign changes like we had for sine or cosine. And it turns out that we can write this as a product of p-values of p times p minus 1, p minus 2, and we'll just keep multiplying products of p until we get to p minus and n minus 1. And that's the n minus 1 we made the observation for on the previous page. Divide it by n factorial times an x to the n. Again, where that n minus 1 is coming from is, for example, on the n equals 3 term, we go out to only a 2, as in 1 less than what n is equal to. So we're still going to have this product of p minus 1, p minus 2's, only going down towards 1 less than what n is equal to for that particular index. So this is the binomial series. And again, this looks a little funky, but again, this is a very compactified notation. So let's do a quick example of this, just to make sure we have our bearings right. So let's consider the function 1 plus x raised to the 1/2 power. And what we want to do is write the first 3 non-zero terms. Well, based on what we have above, in this example, p is equal to 1/2. So anywhere in that above Taylor series or Maclaurin series for the binomial series, we can just replace those p's by 1/2. So we could rewrite this as 1 plus x to the 1/2 it equals 1 plus p times x. Well, in this case, x is equal to 1/2. So it's 1 plus 1/2 x. The next term, we have plus a p, which is 1/2, times a p minus 1. P is 1/2, so we subtract 1 off of it, and then we multiply that by x squared and divide by 2 factorial. And let's just go out another term just for fun. So if we went out another term, the next term would be plus 1/2 times a 1/2 minus 1. See if I can fit this in here. Times a 1/2 minus 2, because the next term after that, when n is equal to 3, is that p minus 2 term. We divide that all by 3 factorial. Oops. And we need to squeeze in an x cubed in there as well. So if we just simplify this down, we have 1 plus x raised to the 1/2. And if we only consider really the first 4 terms of the series, we get to use those squiggly lines, where this is approximately true. It's about equal to 1 plus x over 2 plus, in the numerator, we'll get a 1/2 times a negative 1/2. So we have a minus 1 over 4 all over 2 factorial times x squared. The next term, we'll get a plus. We'll have 1/2 times a negative 1/2. Let's just write this out. Times a negative 3 over 2. All over 3 factorial times x cubed. So we could rewrite this series and do a little bit more arithmetic and rewrite that third term of the series as, instead of plus, negative 1/4 over 2 factorial, just doing out that arithmetic will give us a minus 1 over 8 times x squared, and we could do something very similar for the last term if we wanted. But in general, this is how that binomial series works, how we can just plug in values of p once we know that formula.